I think it's important to note that the Cartesian product is an operation between two sets. And just like when you add two numbers together, you get another number. When you take the Cartesian product of two sets, you get another set. Okay?
Yeah.
And so, for example, if you have the set, the set containing 1 and 2, and then the same set containing 1 and 2, and you want to take the Cartesian product of those two, we just say it's crossed, right? So we'll say the set crossed the other set. Basically, it creates another set with every combination of elements from the original set. So the Cartesian product that I just described would be the set containing 1, 1, 1, 2, and 2, 2. Because those are the only unique objects that, or technically you would have
like
1, 1 twice.
Yeah.
Or 2,
but
1.
No, but 1, 1 would still be the same. Uniquely, it would have that 1.
Yeah.
1
there would
1,
be 2, 1 actually. There would be 2, 1. But anyways.
Oh yeah, flipped version as well. Yeah, because it's a permutation. Yeah, that's very important.
So if you take the real numbers and you take the Cartesian product with the real numbers again, then what you have is essentially ordered pairs of 2 points, with the first element being a real number and the second element also being a real number. Now, we usually take r cross r, we write it as r squared, or we don't
R2,
say squared.
No, actually we don't say r. Yeah,
no,
we say R2.
No,
R3,
we say
R4.
I was just saying it's squared because the 2 is like in the exponential position, but we just say R2, not r squared.
And for any dimension, even Rn, for example, hence the name, we say Rn, like R2000. We never say R to the power of 2000, for example, right? Because it's all simply individual elements of this vector that we make up, or this ordered pair in 2 dimensions, where each of them have individual elements that are different. So the formal definition of the Cartesian product, if let's say we have A cross B, the formal definition of A cross B is the set of all points of A of all points that belong to A and all points that belong to B, as very well you said. Simply all the combination or all the permutations of all the possible points between them. Yeah, it is the permutation. Yeah, for sure. So that product, hence the Cartesian product, will get you.
No, there's one.
Will basically get you all the permutations. Is what I wanted to say.
You have to mention that sentence. Hold on. Sorry. So basically, it's important to note that when you do like A cross B, the first element of your 2 tuple essentially comes from the set A, and the second element can only come from the set B, right? You can't kind of take an element from the set A and put it in the second
no. Obviously. That's the idea of, so even in R squared, or in R2, I just said R squared. In R2, for example, each element would simply be from R, so we don't really think about it. And most of our calculations and everything we do, especially throughout high school and first year we start mixing it up. But throughout high school, we always deal with R2. We only deal with R stuff. We don't deal with these Cartesian products when we start getting into, for example, as I was mentioning before, what if we have the real numbers cross the integers? That means the second number in this tuple of in these 2 numbers cannot be a real number. It must be an integer. It must be a whole numbered integer.
And so if you were to represent this set visually, for example, as Ray said, it's R crossed N, which is the natural numbers. The first element would be a real number. The second element can only be a natural number. And so visually, this would just look like horizontal bars that are separated by integer lengths, right? Because if you were to pick a random, and of course overlaid on top of the real number plane, right? Because any point that is in that set, R cross N, has to be along the x direction. It can be any number, but along the y direction, you are only restricted to integer numbers.
Yeah, and xy, again, like, yeah, technically, if you think about it, like, even using the term xy might not make... Again, xy is just a way to think about these individual representations, right? So when we say the xy plane, like the Cartesian plane, we usually, when we're talking about R2. So x can take any number, y can take any number. So our function can be some messed up function, basically hitting any point on the xy plane. But the moment we have these interesting... like these Cartesian products that are no longer R and R, then we start to see some interesting patterns that functions must abide by. So if a function has a domain or has variables coming from this Cartesian product, we see that it's restricted to certain values, right? And as you were saying, like, if we're talking about R cross N, it's restricted to those integer level steps almost. So all these functions are being restricted via this Cartesian product. So we can do some really handy things depending on the number. So for example, if we know that our variable must be an integer number, so if it's like the number of coffee you have per day, or I'm just making something up, you can't have 1.3 coffees a day, right? It's always going to be integer numbers. Well, I know you can, hypothetically, man, I'm just making something up to make you guys think of that integer number for why we would need something like a Cartesian product. Like, why can't we just use R2?
How many photons do you absorb?
Okay. Well, yeah, I mean, even that is the most perfect integer number question. Yeah, that's it.